Solaris kernel introduced a whole new thing about allocating memory as allocating integer ranges and had this whole object-oriented way of handling those ranges.
I don't think it's related to this because it's not specific to Solaris 10. So we just tested on Solaris 10, but many versions of Solaris actually have the same behavior.
So it's not a VMem. It's not a VMem feature. It was previous in the. It was previous as well.
Yeah. Okay. It's not specific to 10.
Thanks.
So what I was going to point out is that many times when you do a dynamic memory allocation in the Solaris kernel, you're not expected to fail. So it happened that the Solaris kernel fails to actually check the return value of dynamic memory allocator functions. So if when you return null on the size 0, it's kind of a problem. Anyway. Any more questions about that? So while I'm at there, I must say that I did most of the job on I did all the job on all the Microsoft code bases, and many people actually assisted me for the Unix job. So Damien is here. Enrico Perle actually assisted me on the Solaris work, and also thanks to the PAX team, with whom I've done a couple of tests for Linux. Okay, so let's give a couple of examples now that we have done all the taxonomy and everything. This is an example from the Windows kernel, so it's a true example that was fixed. Imagine you have a system call. So in that case, I called my syscall entry point. It takes two parameters. One of them is a p-data pointer. So for those of you who are not familiar with the format of type names in Windows, those are in uppercase, and when you have a P at the beginning, it means it's a pointer. So p-data of type p-struct1, which means pointer on a type struct1, on a variable of type struct1. This pointer is probed. So probe is the equivalent of validating a pointer. So it's like, I can't remember the name of the Linux kernel function for that. It's not copy in user, but something similar, like access OK or something. So basically, whenever you pass a pointer from userland to kernel-land, you have to validate it before you can dereference it. So that's what the probe and read macro does. So you validate that pointer, and then you take the data from that pointer. So cur data dot field 1, field 2, field 3, and you do some arithmetic, but you never validate the value of the field. So the result of the multiplication can be 0. So the count can be 0. Here you have the variable count in third parameter of underscore set data that is 0. So it gets continued. Third parameter is 0 count. And under the same condition that we control with flag enabled. So all examples have been obfuscated a little bit so that we protect the guilty and everything. In the case where count is 0, you have this call user alloc pool. So user alloc pool is actually going to call the same function I mentioned earlier on. So whenever you do a user alloc pool of 0, it doesn't return null either. So if you do if temp equal null return R, it's not going to check any kind of zero size problem. So once you do this, you have the TMP array that is allocated with 0 byte. We've seen previously that it was in fact allocated with 16 bytes. And we do dangling pointer arithmetic. So here we consider zero-sized heap allocated pointer as dangling pointer because you don't really know where they point to if you do arithmetic on them. So save data arrow array becomes a dangling pointer in the kernel. However, when you copy memory with a count, since count is 0, so RTL copy memory is a function of the Windows kernel that is equivalent to memcopy. So if you just take it as memcopy, when you do memcopy of 0, nothing happens. So there is no vulnerability here. If you just look at the code of the syscall straight away, so you might be tempted to say, okay, so I just did 0 size heap allocation, but I don't touch the memory after, so nothing happened. However, if you look at another syscall, you can see that the same pointer arrow array here is actually dereferenced. So if you analyze from a given syscall and you look at functions that are called, the call leader of that syscall, you can see that nothing happened. But if the pointer is stored to a kernel structure, in that case, save data, then it's stored in the kernel and it can be reused in another syscall, and then a memory corruption can happen. So under the same condition here, with a mask on flag enable, you can have indexing of the array. So in that particular case, it's not an escalation of privilege because you can just dereference the memory at an invalid location, so you cannot have code execution. So this is just a crash example, but nonetheless a true example of zero-size problem. Any question on the example? Yeah.
What version was this fixed in? What version of Windows did they?
Actually,
You don't have to answer.
This was fixed in the latest shipped version of Windows. So if you run Windows, a sufficiently recent version of Windows, you're protected of this.
Okay, thank you.
Oh, this is one of the reasons why we obfuscate the examples, because we don't want people to find back the vols. But if you know the Windows kernel a little bit, then it's not too hard either to find which version of Windows I'm talking about and which syscall I'm talking about. So just like put your hands in the dirt a little bit. So early conclusion from our example. When you have a zero allocation, it's not necessarily a problem. Sometimes it's perfectly safe. You do a zero size heap allocation, you don't touch the pointer, nothing happens, it's not a bug. When a real problem happens, it's not necessarily an escalation or elevation of privilege. It can be just a crash of the kernel like BSOD. And also, doing local checking, so say taking a syscall, analyzing the syscall, and going down, sometimes is not sufficient to detect the bugs, because we've seen that we have the syscall, and then we call a function, nothing happens, but if you take another syscall that uses the same data, then a true bug can happen. So you cannot just take one syscall, analyze it, and then do something else. You have to correlate the code review analysis of the multiple syscalls, or do other things that I'm going to present after. Okay, second example. So that was scenario 2 or 3. Here you have same kind of code pattern. You have L param, that is a pointer that is passed to the kernel from userland. So you validate the pointer, so you can see p setting. So all of this again was renamed, so there is no such structure p setting in the Windows kernel, but something similar. You take p setting, the L param parameter, you assign it to p setting, then you validate the address of a field reachable from p setting. So you know that you can read properly at p setting arrow data length. However, you don't validate the value that you read. So if you don't validate the value and you do +1, then you can have an integer overflow and then count becomes 0. So you do zero allocation. Again, you do RTL copy mem with 0 byte, nothing happens, but the PLS structure that was allocated is passed downward. Second parameter of underscore new internal function. Here, the parameter gets renamed to lparam, so we track lparam. And you can see that lparam becomes pstr, and then pstr is dereferenced. So we just allocated a zero size heap pointer, and then we dereference the length field, but we don't know what is the offset of the length field in the structure. So it might certainly be after the safe offset. So cballoc basically the value of cballoc is unknown. You don't know what the value of cballoc is, and then you allocate unknown size buffer, and then of course you copy memory with an unknown size, and what nothing could go wrong here, right? And indeed, once you start to have a zero size heap allocation, then if you start to touch the memory, bad things can happen. You should check this very early in the code. So it's very rare to need a zero allocation. Sometimes you actually need to do malloc 0, realloc, and if you have a loop, so you want to start with a 0 chunk and get the chunk bigger as you go. But like it's extremely rare. I've seen like 1 or 2 cases in millions of lines of code. So in my opinion, zero heap allocation should be forbidden. However, for backward compatibility, this is still a supported behavior in most operating systems, as we saw. So here again, and this time is an exploitable bug because you write to the zero size heap chunk, and of course this triggers a heap overflow. You actually write twice because you do memcopy and then you put the terminal byte. So you have the possibility to write a byte beyond the bound of the buffer. Is this example clear, or does it need any more explanation? Clear? Okay. Okay. So we're done with the first 2 examples. I have a couple of additional examples at the end for near zero locations, but I want to switch to the automated analysis. So the technique we've been using the theorem prover HAVOC is pretty nice, but I'm not going to stick to that. I'm going to present a couple of different automated techniques for automated static analysis or semi-automated static analysis. So I'm not going to focus on the particular tool we used, but have a more general approach to automated detection. So of course we need automated detection for, first of all, because whenever we do a code review, we can always miss bugs. We have millions of lines of code to review. Sometimes we just like overview the code and we say, okay, it looks safe, but we don't have any higher guarantee. So we need actually tools to give us better guarantees. One of the techniques that you can use for automated vulnerability discovery is called data flow analysis. So data flow analysis is a very popular technique, especially in compilers, because it allows you to do optimizations, and you can detect also a good amount of bugs with just using data flow analysis. So what's good about data flow analysis is that it's rather fast. It converges rather fast. It's scalable. I mean, if you do it intra-procedurally, it means within the same function, it's rather scalable. If you do it interprocedurally, it becomes harder, but it's still rather fast and scalable. It's conservative. Conservative means that it's going to compute an over-approximation of the result. So sometimes you're going to say that you have a bug, but you don't have a bug, so it's a false positive. So you don't miss bugs, but at least it goes fast. And what's bad about data flow analysis is that it's all hard-coded, so we have known data flow analysis algorithm either based on intermediate forms such as static single assignment, SSA, and everything. So you don't have a way to configure that. And sometimes also data flow analysis is too conservative. So if you have, say, a merge point, you do if-else, and then you merge. Sometimes you have to merge the information about the data flow analysis. So after you finish with the if-else, you don't know if you come from the if or from the else. So sometimes it's a problem if you want to have accuracy. Data dependence graph. So whenever you compute the diffuse chain, which means the dependencies between variables within a program, you can compute very easily this kind of graph. So here, the blue nodes are registers. It's an example taken from Spark binary analysis tool I wrote a couple of years ago. And you see the white node on the very top. You cannot read, but it doesn't matter. Just follow the colors. The white nodes are immediate values. The green nodes, in that case, are malloc, and the red nodes are free. So with data flow analysis, you can find lots of like easy vulns, such as use after free, or a malloc without a free, or even a free that was done on something that was not mallocked before. So by just dumping the relations between variables, you can actually see if you have a malloc that doesn't lead to a free. So you just follow the dependencies between variables, and you see that the parameter of free doesn't come from a malloc, and this is a problem. So here, the green node doesn't lead to the red node, and you can say, oh, I have a missing free, I have memory leak, or I have a free that was not, whose origin is not a green node, so I have a free that was not done on an allocated pointer. In case you have aliasing problem, which means you don't exactly realize that